possible. Launched in 2022, NQCH was created to ensure Singapore is prepared in this critical field. In our first phase, we established a complete quantum computing ecosystem, covering hardware and simulation platforms to middleware and talent development. We are working with leading technology providers and industry pioneers in finance, in logistics, and the biomedical sciences, developing proof-of-concept solutions that showcase where quantum computing can have real-world impact. Now, as we enter the next phase, our focus is clear: to advance hybrid quantum classical computing, to drive real-world applications through proof of concepts, and to foster quantum talent to support industry adoption. A key part of our strategy is Kibo, a full-stack open-source quantum computing operating system that empowers researchers to deploy quantum-powered applications quickly and efficiently. Singapore's strength in computational biology and its rich health datasets provide a strong foundation for exploring how quantum computing can model complex biological systems, unlocking new frontiers in drug discovery and personalized medicine. The Monetary Authority of Singapore, recognizing the transformative potential of quantum computing in the financial services, has established a dedicated program to address real-world challenges, ensuring Singapore remains at the forefront of financial innovation. As a global trade hub and home to one of the world's largest ports, the ships that surround our shores and the vast stacks of shipping containers are not just symbols of commerce, but opportunities to optimize logistics through quantum-powered solutions. These are strategic areas highly relevant for Singapore and beyond, but we remain flexible and ready to explore new directions as promising opportunities emerge. As quantum technology gains traction, companies will need to upskill their teams and attract quantum talent. At NQCH, we are committed to building this ecosystem through initiatives like Q-Talent, an accessible online platform offering courses for learners at all levels, and workshops tailored for companies looking to learn quantum computing. Quantum computers will not replace supercomputers. Instead, their true potential lies in working together. With compute infrastructure from the National Supercomputing Centre, Singapore, we are benchmarking hybrid solutions against the best classical alternatives and exploring their impact for the industry. To bring this vision to life, the Hybrid Quantum Classical Computing Initiative, launched in 2025, will integrate quantum and classical computing resources supported by enabling middleware. The National Quantum Computing Hub began as a proof of concept, a bold step towards building Singapore's quantum ecosystem. Now, with a strong foundation and a growing network of industry and research partners, we are driving the momentum needed to position Singapore at the forefront of quantum software and applications.
Ladies and gentlemen, our next session is brought to you by NQO and NQCH, and our session is titled Latest Developments on Quantum Hardware. I'd like to welcome our esteemed panelists and also our moderator to come on stage right now. Put your hands together to welcome Program Manager of the Center for Quantum Technologies, NUS. Our moderator is Miss Vanessa Koh. A round of applause for Vanessa. Thank you, Vanessa. All right, Vanessa, over to you to moderate the session, and a very warm welcome to our panelists as well. And of course, ladies and gentlemen, please continue to send your questions in. Thank you.
Thank you so much. Good afternoon, everyone, and welcome to the panel on the latest development on quantum hardware. Dr. Raj has already given us a great introduction, so we're all excited. And I'm Vanessa, as introduced. I'm a program manager of the National Quantum Processor Initiative here in Singapore. And it brings me great joy to moderate a panel on hardware, which is something I'm really passionate about. And it brings together 4 brilliant individuals who are involved in the quantum hardware space from many different perspectives. So to jump right in, I'm going to get them to introduce themselves. So I want for our panelists to tell us, who are you? what company do you represent today, and a key takeaway that you hope for our audience to gain from this panel today. So I shall give some attention to that side of the stage first, maybe. So let's start with Dr. Tom. How about you go first?
Hi, thank you very much. Good afternoon, everyone. It's a real pleasure for me to be here today. My name is Tom Darras. I'm CEO and co-founder of WeLink. WeLink, we are a leading quantum networking company based in Paris, in France, and we provide all the networking solutions that are required to deploy interconnected quantum computers in data centers worldwide. So my key takeaway for today will be that quantum technologies need quantum networks. We need to build the infrastructure to scale quantum technologies from quantum computing, but also for the quantum internet. And WeLink is providing the solution to scale these technologies.
Hi, good afternoon, everybody. I am Maud Vinet. I'm CEO and co-founder of Cobly. Cobly is a French quantum hardware startup, so we build quantum computers and we build the software that is mandatory to build your applications. What is original is that I made my PhD 25 years ago in quantum physics and switched to the semiconductor industry. And what we're bringing in Cobly is that we're bringing accessibility to quantum computers. We are democratizing quantum computers thanks to the semiconductor industry. Basically, you remember the revolution when we switched from valves to transistors? That's what we're bringing. We'll leverage the semiconductor industry to produce billions of qubits at an accessible cost.
Good afternoon, everyone. Thanks for coming to listen to us. I'm Matt Hutchings, Chief Product Officer at Seek, and we build quantum computing on a chip architecture to run and ultimately help to scale up any quantum computing system that's out there. And I think my key takeaway is today, quantum computers have vast complexity, but ultimately it's amazing that we can build them. So key takeaway is that they are happening and they're very, very real, as we heard from the fantastic talk from Raja earlier. But today, they still face significant challenges to scale, and a lot of that is built into their hardware complexity. So I think takeaway being, we know how to scale computers. It was integration on chip, eliminating a lot of that overhead complexity and building everything onto a single chip. So let's take those lessons and build that into quantum computing, and then ultimately start to scale up to where the industry needs it to be.
Hello, everybody. My name is Chris Langer. I'm a fellow at Quantinuum and a hardware architect. I focus mostly on how to build the next generation machines. And Quantinuum is an ion-trap quantum computing company. You just heard Raj talk about it. And I think the main thing that we offer is we offer usable quantum computers today that work, that solve problems that cannot be solved any other way. And the future is very bright because today you can use it for solving the problems of actual relevance, and we're really on the tipping point or on the verge of doing something extraordinary, and the next generation machines will really enable that in a much bigger way.
Perfect. Thank you so much for introducing yourselves. So we'll jump straight in, and before I do so, I'll remind our audience that you can send your questions via Pigeonhole, and hopefully this classical technology will enable me to receive it and transmit it to our speakers, so do join in. But I would like to open the discussion by asking for your opinions on what you think is the greatest success and the greatest shortcoming in hardware development at this juncture. So I'll open it to anyone who has a burning desire to jump straight in.
Maybe I'll kick off. I think, I said it in my introductory that the greatest success is that we've built quantum computers, and not just one or two. We've built many, many quantum computers. There's something like 150 on the planet plus, and impressive quantum computers that can do real, tangible work. And so I think the most impressive results we've seen recently are around demonstrations of error correction, and the fact that they ultimately have overcome the boundary to say they can now scale. We know fundamentally we can make them very, very big. The shortcomings are that they are still very difficult to engineer and complex to build, and that goes back to we need to figure out how to actually take them from the prototype stage and build them out. And that I think is needing a lot of maturing of the supply chain and less vertical integration that you see in the manufacture of these quantum computers, and looking at how do we actually build towards a mature supply chain that can deliver these things en masse at scale.
Can I bounce back? Yeah, well, I will repeat because I think that needs to be underlined. We are at the stage where we've got all the pieces of the puzzle. Raj said we have identified applications. We have now software companies, and in Singapore you've got some compiling companies. You are really good at software. We also have demonstrated quantum error correction in a lot of modalities, and what is new is that now we're also bringing in the industry, and that's going to be my tipping point at least. We're bringing in the semiconductor industry that was busy with Gen AI chips and is now looking at quantum. And what we've done is that we have managed to bring them in to produce billions of qubits. So to me, this is very exciting because it will be a speed up. We're at this tipping point. Shortcomings is that we're still missing engineers, and we still miss a critical mass to democratize quantum computing and make it accessible, do the relationship between classical computing and really have a massive adoption. But I think that the reason why we're here today is just to provide enthusiasm and bring people in the adventure.
Let me add to that error correction. I think one key piece of the error correction is that it actually works. Right? I think the theory of error correction has been around a long time. The basic concept is to try to encode with redundancy the information that you're processing and operate on it in a way such that it's robust to errors. And this concept is supposed to make the errors in the logical qubits be much lower than the physical qubits. And many of the demonstrations that have been done have been kind of proof of principle demonstrations. But I think a key major result that we have achieved is that we can show that the error correction actually outperforms the physical counterpart operations. And so that's something I want to add on the error correction side. But I also think it's really a really key takeaway that we have as well, is that we're actually solving problems today, even on the physical hardware, that cannot be solved any other way. Earlier this year, we actually simulated a quantum magnet, right? And it was in a regime where no supercomputer could actually solve it. We're able to see phase transitions in the phase diagram, and this is just the start for being able to do new material discovery. So I think that's something really exciting to look forward to. In terms of drawbacks, in terms of what you need next, I'd say we just need additional technology development for some of the subsystems in order to help us scale. But that activity is ongoing, and you should look forward to seeing good promises to come there.
Yeah, so to conclude, I'm quite aligned with what everyone said here. So the first point is the tech is advancing extremely fast, and that everything is accelerating as we are moving forward. I think the results that we mentioned on error correction recently, I mean, I didn't expect this to occur so quickly. The second one is on top of the technology and the research. The technology is today mature. We have quantum computers as products which are being sold and deployed around the world. And then the thing I believe that we should keep working on as an industry is how do we go beyond now deploying individual quantum computers. The vision for WeLink is that we need to deploy several quantum computers interconnected in data centers, very likely in heterogeneous architectures. So we'll need to work all together as an industry to ensure that this happens in the very short run.
Thank you all. That's very insightful responses already. So I love that you guys brought in error correction in addition to scalability. Maybe I want to draw it big picture again for the audience to kind of like ground it back to why do you think so many different hardware platforms are still being explored at this point? So we have heard about trapped ions. We know there are chips. I want to throw back neutral atoms into the discussion. So why do you think this is still a point of exploration, or do you think that we are at a phase where we can commit to a certain hardware platform of choice. So each may have their own like partiality in this case.
Who's the least biased?
Well, I'll give an unbiased answer. I mean, the answer is because the marketplace will decide which technology is going to be one that's selected, and it hasn't chosen yet because people are still figuring this stuff out. You know, we need to scale, and there will be a well-defined winner, I think, in the future, and I think the marketplace will decide which one that is.
I will bring a perspective of technology development and what makes technology adopted, and I'm fully in line. That's the market which choose at the end. But what's happening is that we have all the technologies have some drawbacks and some advantages, and nobody has won yet. And the technologies that are today accessible and that deliver computers, their scaling path is not obvious. And there are technologies which have a scaling path that is obvious. And we today, every day, we manufacture millions of qubits. And we do today manufacture millions of qubits. But we're late because we started late, and it takes time to leverage silicon because there are a lot of rules that needs to be respected for the industry. So we are not delivering yet on the promise, and that's what is making the market just looking at everybody and waiting for the scalability signal.
Well, maybe from my perspective, because I'm not selling quantum computers, so I guess I might be not biased in this way. But still, the way we see it at WeLink as a company is that we believe that some quantum technologies in the hardware might be some better suited, for example, from some specific application or use cases of quantum computing. We are not yet there, but there might be some technologies better suited for optimization problems, some technologies better suited for complex simulations. And the way we see it at WeLink is that we are not choosing the technology. We are developing quantum networking solutions which are multi-platform by nature, meaning that we can deploy several machines based on a variety of technologies, so that depending on the use case we want to achieve, we can actually allocate the computation to the best computing part of our network. So that, I would say, our strategy for WeLink, as of now, working on multi-platform. And of course, if the market chooses a specific technology, we'll be able, of course, to provide our solution to these partners as well.
Yeah, I'll echo a lot of what's being said here. But you know, our technology, we build chips to run quantum computers. We have chips that we work better with, but ultimately we can work across the qubit architecture. And I think it's actually quite exciting that we live in a world where there's so many different types of quantum computing platforms still being developed. And I agree, you know, ultimately the market's going to decide, and we need to be prepared and running all of them, and they all have their own individual challenges and advantages, and there's no, I don't think there will ever be a winner. I think there will be, you know, lots of different, you know, it's very complex to build any computer, let alone a quantum computer. So there may well be some mixture of quantum computers in the future, or it may be some that are better for certain things or different applications. But you know, going back to the market point, ultimately what's going to drive value is they do something interesting and they do something powerful. And so the first quantum computers that do that will probably take a lead, and then maybe as the market matures, other technologies will come along and drive even more value. But it's ultimately that's what's going to decide, you know, if there is ever a winner, which I don't think there will be.
And maybe to talk about the market, we will change KPIs. We will change figures of merit. And it's nice that you brought in the market. When we started building quantum computers, we started from physics perspective. So we were looking at the coherence time. We were looking at the fidelity of the qubits. Because you've got to pass a certain level before you get credibility. And now we're at a stage that all the modalities are just more or less have passed this stage. And now we can talk about the market, and what the market will look at. It's your ROI. How much does quantum computing cost you? How much does it bring you? How many, if you've got $1, how many giga quantum operation can you perform? And that at the end of the day is what's going to make the difference, I believe. So we're going to start looking at a different angle. We enabled quantum computing. Now we've got to really deliver ROI.
Maybe I can follow up on that. I do think that, you know, in some future state, when many modalities can make a quantum computer that actually works, then your metrics are going to be things like cost, right, and value divided by cost. But that's not where we are. The metric that matters today is, does your computer work? Okay. And our computers work, right? They actually produce answers that are right. And I don't think all the modalities have really passed this threshold where everybody has great fidelity. I do not think that's true. I think you really can rank them on fidelity, and I think we come out on top.
Okay, that's getting exciting. We actually have a question from the audience that I want to throw in, which is actually quite applicable right now. So someone's asking, could the move toward modular or networked quantum processes lead to a quantum internet? And what are the hardware bottlenecks in general, if any?
So I guess I can answer that question. So indeed, the idea of modular quantum computing is that we are creating interconnection in the quantum regime between quantum computers, and what we are doing here from the physical perspective is that we are creating entanglement between devices. And then we can do that at local area networks within data centers to interconnect quantum computers. But we can also make it so we share this entanglement over larger and larger distances in quantum networks, and this is the application which is called the quantum internet. So actually at WeLink we are working on these two applications, quantum internet more for quantum safe applications and modular quantum computing for data centers. And I would say for that you need to develop very specific technologies both on the hardware and the software layer. I can mention, for example, on the hardware side, we need to be able to create very efficiently this entanglement in the network. And to do that, you need to have access to entangled photon pair sources. You need to be able to distribute this entanglement very efficiently. And for that, there's an amazing technology that we have developed at WeLink, which is called the quantum memory. It's typically a device that allows to buffer quantum information and route it very efficiently in such network. We have demonstrated the world most performant quantum memory, which was actually the starting point of the company 4 years ago. And after only 2 years of development, we have transformed this quantum memory, which is now available as a product. So we have several of these quantum memories which are deployed and sold around the world. So if you are also interested in deploying quantum memories, feel free to contact me.
Maybe just off the back of that, I think quantum networks are important and we should be developing the infrastructure, but we also need to make very big individual quantum processors. They may themselves have a modular element because building very high fidelity, very performant qubits is very difficult at any kind of scale. But my key takeaway is that yes, we should network a quantum computer, but the quantum computer itself needs to be as big as we can physically make it. And we shouldn't say, let's build a small quantum computer and then network them all together, because then we're going to solve everything, which some of the industry thinks is a route. And I don't believe there is any value in lots and lots of very small quantum connected computers. I think we need to build big ones and then connect them, and then we'll have value.
Well, of course, I do agree, and that's what we've learned from the past. From classical computing, we've seen that we grew the curve as big as we could, and when we were stuck, we started working in parallel, and then we discovered new algorithms. That was a real breakthrough, but we need big cores, big quantum cores, to be later on interconnected.
That's a great insight. Maybe I want to draw back to this person's question because they really asked specifically about quantum internet. And I think, the internet they have in mind is probably like, going on Google and being able to actually like run questions like this straight away. Like, how feasible is that at this juncture? How should we actually envision or think about it in the quantum regime?
Maybe I can introduce. So the concept of quantum internet is really, as I mentioned, this capability to transfer quantum information in networks. And with access to this information, we can run some applications which are beyond the reach of conventional networks, secure quantum communication, distributed quantum computing, or distributing sensing are the main application of the quantum internet. But in terms of application and usage, the way we understand it is that the quantum internet is not going to replace the conventional internet. I believe there's no particular reasons why each of us individually should be connected through entirely quantum-safe network for our daily usage. So the way we see it is that there will be dedicated infrastructures that will be complementary to the conventional networks, where here for some specific institutions, government bodies, financial sectors, healthcare, you will need to make use of these quantum-safe infrastructures. So we are very involved in also deploying such quantum-safe infrastructures. We are part of many initiatives, in particular at the European level, where we are also onboarding end users of quantum internet in our projects.
Just one add is, I do think one of the main applications for the quantum internet is blind computation, right? This is a concept that the user can obfuscate what computation they were trying to execute and send it to the quantum computer to execute, and the quantum computer actually never knows what they're actually processing, and the data comes back. This is a pretty far-end application, and I think for regular communications, I think classical communications with classical encryption, I think is pretty safe.
Amazing. Maybe I would now like to invite you guys to share a little bit more about, Dr. Raj has mentioned about Gen AI. What are your individual thoughts on the relationship between AI and quantum computation in general? Like, are there lessons we can learn from the development of the AI trajectory? How do you see them working together? Just your thoughts in general.
Well, I'm happy to kick off. I think there's kind of two prongs to this. That what can AI do for quantum computers, and what can quantum computers do for AI? And I think the first camp is where we'll see the first value that I think AI can help us, build and manufacture qubits and better quantum systems. They can help us calibrate them. They can better help us build compilers for them, and that may be very important to realizing very large-scale quantum computers. I think ultimately, a lot of the problems that the AI is potentially solving in quantum computing can be also solved at the hardware level, so we should be looking at both. But I see that's the first way that they can work together. But then I think what people are most interested in is the back end, which is, what can quantum do for AI? And I think, the first scope that we see there, and I think Raj talked about this a lot, is quantum as a kind of a preloader into a large AI model. So can quantum computers make it more efficient for a large classical computer to do and run a large LLM or language model or something like that? And I think that might have the first benefit, and I think there's even quite clear advantage that can be driven there, and even application use cases that are pointing in that direction. And then the kind of moving beyond that of can you run full quantum AI, I think there is huge potential for that. It's a bit more uncertain. It's probably a bit more future looking. But if we can achieve that as an industry, there will be enormous impact at that stage.
When I think of Gen quantum AI, I really think of it as it's a great way to efficiently use the quantum computer to solve the problems that you want to solve. So you can, suppose you wanted to design, a new molecule, and you wanted to simulate this. You, in principle, could code this up on your quantum computer and simulate it. But usually, the discovery process involves doing multiple iterations across different parameter sets on a family of models, let's say. And to do that, it takes a lot of quantum compute time. The benefit here is you can sparsely sample this parameter space and then train your AI, and then use the AI to do inference all over a ton of different spaces. And so it really enables you to kind of efficiently use your quantum computer to solve the problems of interest. And so it's a really big enabler for the near term.
Yeah, maybe to wrap it up, we talk about synthetic data. What quantum computing can provide is synthetic data, make the compute the data that we don't have currently.
Yeah, I think that contribution of synthetic data is a big thing. And actually, you guys have already subtly answered a question from our audience, but I do want to acknowledge it. Someone did ask, will quantum computing hardware have a ChatGPT moment of having a strong enough machine appear? And if yes, how long will it come? So I don't know if you guys have further thoughts to add on to that, because you've kind of already shared a bit on that.
Maybe I can complement, not necessarily thinking about the moment on which quantum ChatGPT will arrive, but just thinking about the lesson we learned from the ChatGPT moment. It was that the persons who were not there at the moment, I mean, they lost the race completely. And so you don't want to be in a position to start working on quantum at the moment where everything accelerates. And I think we are at the moment where this is going to arrive very soon, and sooner than we expect. And so we need to ensure that we are ready. And I think if you are potential end users of quantum computing, you should start working on quantum computing from now on, working on the first machine which are available, making sure you can develop and adapt your use cases to make sure when everything accelerates, you will be competitive and ready to follow.
I think we're at the precipice now. The key precipice is really to be able to do something that you couldn't do another way. And I think that we're there now. But the reason it's a little bit different than a ChatGPT moment is ChatGPT surprised everybody, and then it caused widespread adoption. And we haven't seen that yet, right? So I think we're kind of at maybe the precipice of maybe next generation machines possibly letting that happen.
And I would say that it's going to come fast. As we said, we're speeding up. Currently, there are some niche problems that can be solved. I would say that maybe what the audience had in mind when we talked about the ChatGPT moment is when there is no controversy, when in 2 years from now, AI cannot catch up, or classical computers cannot catch up with quantum computers. And this is coming. And we all have our roadmaps. All companies have a roadmap where they will deliver 100 logical qubits. And I believe that's when the real ChatGPT moment will happen. And for us, it's at around 2030. That we will deliver, and then we've got a roadmap where we go beyond thousands of logical qubits because we know how to make those qubits.
It's a very difficult question around the ChatGPT moment, because it was partly because it was very consumer-led, and I think the real value of quantum computers is it's going to be quite industrially led early on. So I think the first ChatGPT users will be, industry end users, and they're not going to be as vocal as people on their phones. So I think there will be a ChatGPT moment, but it will be, investors getting very, very well off, and industry end users finally be able to make some return on investment. So it might not be as fanfare as ChatGPT moment was, but I think it will happen.
Yeah, so it's not going to be so much of like me asking ChatGPT like which planet's in retrograde, that's why I'm sleeping badly. But that brings to another question that our audience members has shared. It says, as end users, to be the first few to adopt quantum technologies under the NISQ era, will we gain more early mover advantage, or will we incur more first mover cost? So I think they're asking more on opportunity cost. Is it best to jump in, or is it more costly to jump in now?
Well, I guess we all agree that you've got to jump in. Well, I don't know. I let you guys answer. But you've got to jump in now. And for the obvious reason that it takes a long time to develop algorithms and to suit them to your applications. So as of today, it's mostly R&D departments that are concerned by quantum computing, but if you got involved now, it will be customized for your applications, and you will be in the early adopters, in the early movers, so you will get the benefit at the end of the day. And regarding the cost, there are currently a lot of support, and we're at a stage in the semiconductor industry that's really what we did when we developed a new technology. We pair with the ecosystem, and we share the risks. And currently, we're at a stage where this co-petition exists, where we're moving as an ecosystem, we're building the bases, and we're sharing the costs and the risks to move forward. And then when it's de-risked, you go on your own. And well, that's my perspective. Let's go now.
Yeah, I mean, completely agree with that. I mean, we heard yesterday from various end users that if you're developing an application that you want to see ROI in even a decade, it's already been under development today. We need to be jumping in straight away. It's a new paradigm of computing, so it's going to be challenging to get that into your workflows. So should be focusing in on now. And Raj mentioned earlier, there's some fantastic companies like Quantinuum out there that are making quantum computers more accessible. So I think the barriers to entry for these companies and end users is getting lower and lower. So I think the opportunity cost is significantly reducing. And will be made better by quantum computers becoming more manufacturable and cheaper to operate. So I do think, you mentioned earlier that we're not there yet for cheaper quantum computers, but I think we need to be pushing in that direction so we can lower that opportunity cost so that more users can jump on at a lower cost point. But I think, yeah, you should be looking now, even if it's going to take a while to develop the applications.
There are trends that are to your benefit. The resource cost for applications is coming down. Right? Probably a couple orders of magnitude every year or two. And so that means the earlier you get in, the earlier you get to capitalize. And the second thing is you have optionality. You might discover something that you won't discover until you try. Because everybody here would agree that the applications you use on your phone or on your computer weren't invented before the computer existed. Right? And so once you have a quantum computer, now you have the opportunity to develop. And I think that's another reason to get in right now.
Lots of enthusiasm stirring here. Hopefully our audience member got the answer they wanted. I'll follow up with the question by saying, where do you guys see the need for more innovation outside of the existing systems in place? So, we talked about how we're moving from a physics problem to an engineering problem to a computational problem. So are there any other gaps right now, be it in research or in industry, where you think more innovation or new innovation is required?
I'll give a brief answer. I'd love to see more innovation on the application side, right? If we can get more applications, that's going to bring more value to these machines. It's going to bring more value to you as a user, and so I'd say jump in there.
I'm going to go the opposite end of the stack. I think today's quantum computers were built by physicists, and we need engineers building quantum computers. And so I think the key challenge is stop building them like they're massive science experiments, and start building them like computers, and build the technology and infrastructure and a mature supply chain that's going to deliver that.
Well, I was about to say that, so I'm going to take it from the human resource perspective. I think we need innovation in teamwork, because we are bringing physicists and engineers together, and sometimes we do not speak the same language. So innovation in human resource, in thinking multidisciplinary work is going to help to move forward.
So I have to complement that now. I guess I will go back to my field of expertise, but I think we invested a lot of resources in developing the first generation of quantum computers, and that now the industry is maturing, that it's not just going to be QPUs, but a lot of things around application, supply chain, enabling technologies, software, but then definitely networks and preparing the infrastructure for welcoming this technology. So yeah, I would say these are where we should innovate here.
Want to kick back on that, Chris?
No, I'm happy with my answer.
You have your answer.
I mean, applications, we should be developing them because the better they are, the easier it is to build them, the quantum computers.
Yeah, I was going to say that actually innovations in applications does make sense because, you know, we started with building quantum processors and all because we could simulate materials and all because they are quantum, right? So if we can actually get applications that are completely outside of quantum regime to begin with, it could be a whole new era. So maybe that brings me to another question. This one may be a bit random, but we'll see what we get. If money wasn't a limitation, what is one wildcard technology you would bet on that could revolutionize the trajectory of quantum hardware development right now?
If money wasn't an object, I would say diversifying away from the current computer architectures that exist. So we are a CMOS-driven society and world. And I think it's been shown that CMOS is pushing the limits of what it can do both computationally today and also how it can support potential quantum computers. So we need to diversify away from CMOS, look at alternatives. I'm partly biased that we're looking at single-phase quantum logic and other superconducting logics. But though cost is a barrier, it's not a huge barrier that I think the world has driven down the CMOS route, but it won't take a significant cost to start looking at alternatives. So though it's a cost barrier, it's not a money, we don't need unlimited budgets to do this. We should just be doing it.
Maybe just a slight counter, is I think the ecosystem is exploring all of the avenues. This is the R&D ecosystem, right? And it's at different scales, at university scales and company scales. And so when a new idea comes out, it is being tried, right? And I think what's happening is you're just seeing the maturation of the industry. It's kind of consolidating around a handful of technologies that seem to be a little bit more favorable. And I think that's a natural thing to do.
Got tons of money? Not a problem?
No. If money were not a problem, well, we would already have millions of qubits produced in Silicon Foundries, and they would fit on a 1 centimeter square. And today, if money were not a problem, I would definitely ask the material suppliers, the tool suppliers, to develop materials that we need to make the qubits reliable. And today, this is going back and forth. We hit milestones, and then they improve the materials, and then we hit new milestones. But I would put everything in parallel so that we've got a quantum computers with thousands of logical qubits within 3 years from now.
So if I had unlimited money and energy, I think what I would do is that I would build what our customers are dreaming of. Namely, I would build a data center in which I would deploy interconnected quantum computers that would be itself interfaced seamlessly with conventional computing in hybrid framework, and then I would give access to this infrastructure to customers of quantum computing. But then one thing still to mention is that, of course, money, energy are required resources, but we still need to consider that we have some engineering challenges, we have still some physics challenges and good ideas we need to think about as an industry, and it's not always just money, but you need also to have the smart persons within your team to unlock all these. And I think that's why we are here today. It's because we have managed to do that, and we transform the scientific challenges into engineering problems. So that's our vision here.
I just want to add to that point. I think the money no object question is we're back beyond the precipice of quantum computing. We know we can build it. It's an engineering problem. It's an incredibly hard engineering problem. So if money was no object, pour money in. If you want quantum computers, they will come faster with more money. That's the stage that we are in the industry. So money is an object, but I think that the point is, the more we invest, or the more the world invests, the quicker quantum computers will happen, and potentially will put less strain on Earth's resources around energy and other aspects.
Yeah, just to add to that, I think one area where you would spend it is on the supply chain, and doing engineering to reduce swap, size, weight, power, and cost. I think that's one key area I think could benefit everybody.
Wonderful. Yeah, so investors, if you want to pour in money, do pour in money. And maybe we have a bit of time left. I want to draw back the idea to people. So we definitely always need talented people to come into the field. So if a young founder or a young student came to you today asking about quantum hardware, what would be your advice to them at this stage of the development?
Off the back of your comment, we still got a lot of swap problems at the manufacturing scale, and maturing of the supply chain. So find a specific technology that you can develop within the supply chain and go after that, because as the technology matures, large system integrators and developers will be looking more of the supply chain to build in those components. So I think there's an enormous opportunity for founders and smart people to get out there and develop new companies that can do cool stuff.
I would advise to go bi-disciplinary, go with a little bit of quantum and go with a little bit of engineering, or go with a lot of quantum and go with a lot of engineering, because you will be very valuable at the boundaries, and we need more people being bilingual in quantum and in engineering.
So if I were to meet a young founder, I think of course, the natural thing that people starting companies should do is try to make something which is unique and which is not already existing into the ecosystem. So given the progress of the industry recently, I think I would not necessarily target to, let's say, develop a new quantum computer with a full stack approach, because that's something I would say which is quite covered, except if you have an amazing technology which is outperforming all the others, of course. But then, yeah, try to investigate what are the missing elements in the industry. We talked a lot about the application, the software layer, supply chain, and also, thinking about you can do quantum, but maybe if you can onboard other type of application and AI in your project as well, I would recommend to go in that direction.
Okay, amazing. So to wrap up our panel, I would like to go back down the line and ask everyone to say in one sentence what you hope for the audience to think about after today about quantum hardware when they reflect on this.
You should jump in today. The computers today are doing amazing things, and you will be ready for tomorrow.
Yeah, I mean, exactly. Quantum computers exist. It's not a sci-fi problem. And so the takeaway is they're very real, and you need to start thinking, how can I take advantage of this new technology? Because that will ultimately drive value and help us build quantum computers faster.
And I definitely agree. Think of applications. And I would say talk to people developing hardware, because we're still at a stage where applications can help design hardware. And there is still a lot of dependence between hardware and application co-development. So this is your chance.
And to complement, so we discussed a lot about quantum hardware for quantum computing here, but of course quantum is bringing value beyond quantum computing itself. We discussed briefly about that, but quantum networks, quantum safe infrastructures are also things on which we require very exquisite hardware. And to complement also on this application and this topic, the hardware is ready. You can make use of these technologies and make use of them as early as you can.
Thank you so much, all. So this has been a very fulfilling discussion. Can you all help me thank our panelists for their time and their insights? And we'll now hand you over to the next panel. Yeah, we'll be off, I guess. Talk to them if you have ideas, and stay for the next panel on quantum algorithms. Thank you so much.
And of course, a round of applause for Vanessa as well for doing such a great job preparing such interesting questions for the panelists. We welcome you to join us downstage. Thank you very much, Vanessa. And ladies and gentlemen, I hope you're having a great time just listening to the content, the stories, and getting inspired. Please stay for the next panel discussion, which I'll tell you the title right now. So we covered the hardware. Now we're going to talk about algorithms from, of course, today's noisy intermediate scale quantum, which stands for NISQ, the strategies to the possibilities being unlocked by fault-tolerant quantum computing, which is FTQC. So the title at hand next is going to be on quantum algorithms from NISQ to FTQC. Our panel of industry experts are ready to, of course, come on stage to talk to you. Ladies and gentlemen, I'm going to welcome our panelists to come on stage right now and to welcome our moderator,